Great. So, the final presentation in this session, specializing data access in a distributed file system, and the speaker is Pratyush Das. Did I pronounce that right?
Yes.
Okay, okay, please go ahead.
Thank you. Hi, my name is Pratyush Das. I'm a PhD student at Purdue University, and I'm going to be presenting work done by me and my co-authors, Anxhelo Xhebraj and Tiark Rompf, on how one can use generative programming to specialize data access in distributed file systems. So there are a lot of distributed file systems out there, such as HDFS, Ceph, Lustre, GlusterFS, and many of them being integral parts of popular system infrastructures. For example, Apache Spark used to use HDFS as its main storage layer when it first came out. But what are the challenges with distributed file systems? Storing files on a distributed file system are not always as straightforward as storing it on your local storage. A typical operation over a distributed file looks something like this, where you have an API call to load the file from your distributed storage into a buffer, and then you perform some operation over it. But although these API calls look very innocent, there's a lot going on under the hood, as you might imagine. First, the distributed file system topology needs to be queried. Usually a file stored on a distributed file system is not simply a contiguous block of bytes, but stored in some special way. After that, several workload decisions need to be made, like deciding which node to read a particular chunk of the file from, figuring out which part of the file needs to be read from which node, and minimizing any data race conflicts if that needs to be handled. Then the file is read on the local node where it is stored. The user-specified computation is performed locally on the node that a particular chunk is stored on, depending on whatever workload decision was made. The computed data is moved back to the client, and then any synchronization or aggregation happens to compute the final result. But all of these things are happening at runtime. And while doing it at runtime has its merits, maybe it's not always necessary to incur these runtime cost overheads. Especially the first 2 points that I've highlighted in yellow, querying the file system topology and making the workload decisions, maybe these can happen before the actual program execution even happens. To solve this problem, we can imagine a world where if the user wants to operate over a file stored in distributed storage, they can just provide the name of the file, and then a compiler would be able to figure out the distributed topology as well as make the workload distribution decisions and generate a program that is specialized to such details. And in this paper that we are presenting today, we talk about how we make this happen. For this presentation and our implementation, we decided to choose HDFS to demonstrate the capabilities of our system because HDFS is open source, HDFS has easily visible abstractions, and being around for so long, it's a very well-studied distributed file system. To motivate the problem, we start by looking at how distributed files are laid out in HDFS. So HDFS comprises of a name node that stores information about the distributed file topology and several data nodes which actually store the data. An HDFS client creates a new file by giving its path to the name node, which makes decisions on how the file should be split up into blocks. Now for each block of the file, the name node returns a list of data nodes to host them or host their replicas if required. The data nodes then eventually confirm the creation of these blocks and then sends this information back to the name node. For distributed systems built on top of an HDFS cluster, for example Spark, the workflow looks something like this. The master node asks the cluster manager to operate over a file stored in this distributed file system. The cluster manager then sends this instruction to all the available worker nodes. Each of the worker nodes then query the name node for the most up-to-date file topology of the distributed file system for the file to be operated over. The name node then communicates with all the data nodes to figure out how that file is split up, how and where the block should be loaded from, basically the workload decisions. and then communicates this information back to the worker nodes to let the higher level system built on top of this now be able to make workload decisions based on this information that HDFS has decided to pass on. Now, finally, the worker nodes can directly issue instructions to load parts of the file from the various underlying file systems where parts of the HDFS file are stored. This is an entire snapshot of the communication pipeline that I just described. But as we noticed while we were walking through the steps, the phases highlighted in red on this slide can potentially happen before the actual execution of the program in certain cases. It is possible to query the name node for the most up-to-date file topology at compile time and generate appropriate specialized code that is aware of the file topology and can load files directly from the underlying file system, bypassing any notion of Hadoop altogether. And if we are able to do this sort of specialization and query at compile time, our high-level system can look like this, where we now have specialized worker nodes instead of different worker nodes and data nodes. And these specialized worker nodes can handle the data movement and the data loading directly from the underlying file system. And as we can see in this figure, there is no longer any notion of Hadoop or API calls to the Hadoop interface. There are just blocks of data on different file systems that are being loaded from. If we take one step back, this is what our operation actually looks like. Given an input program f that takes in 2 arguments, an HDFS file and the operation over the file, we can generate fx, a function that is specialized to x and takes y as an argument. We call this staging. And how do we design such a system to perform such specialization and staging? We use a framework called lightweight modular staging, or LMS, as we learned earlier during this session. I'll just quickly walk through a simple example in LMS to demonstrate how it works. Let us consider this unstaged interpreter for arithmetic expressions that I have on the slide. This interpreter eval takes the ST of expressions E and an environment sigma and evaluates the expression program to an integer, int. The staged version of this interpreter adds the annotation rep to the environment type and the result type, indicating that these are values that are going to be known at a later stage. So for this sample ASTP, which adds a constant to a variable x, since in our interpreter E was a first stage value and the environment was a second stage value, we can see that we can unfold the recursive function calls and eliminate the static computations over P and generate a specialized interpreter eval P that sums the concrete value 3 to a lookup into the map for the variable x. So using LMS, we build our system called DDLoader, which stands for Distributed Data Loader. And the code presented on the slide is what is the interface that is provided to the user to program using this. So HDFS exec is a function that provides an array that contains the paths to each of the blocks that make up the HDFS file. As you can see, the paths array is annotated by rep, which indicates that these values are going to be known at a later stage. However, the user can still write iterators and perform operations over this variable, with the only difference being that the actual values are going to be filled in later. The user provides the actual operation to be performed over the HDFS file in this HDFS exec function, and they then create a DDL driver object with the operation, the name of the file, so on and so forth, to generate code that is specialized based on this HDFS exec function. Let's look at a simple program written in DDLoader to demonstrate how our system works. This is a simple whitespace count program. So the user creates a buffer to read the contents of each block of the HDFS file into. They then write a loop to iterate over each block. Something to note here is that since we provide a per block programming model, the user can choose to only operate over some blocks of the file. And this becomes more important if the user writes some conditional that would filter out the number of blocks that you're operating over, which would reduce computation. They then open a file handle to read the block. and then use the read func function provided by DDLoader to read the contents of the block into the buffer. For our evaluation purposes later on, we will see that the read func function call generates a memory map call, but it can be configured to be anything else. For example, a simple read system call to load the bytes into the buffer. They can then express any arbitrary computation over this buffer, in this case, a simple check that iterates over all the elements in this file to see whether it's a white space, and if it is, then increment a counter. Let's look at how the user would write the same operation using Hadoop's canonical Java API and compare it to the program that we just wrote in DDLoader. So similarly, the user allocates a buffer to store the contents of the file. They set up the Hadoop environment to load the file from the underlying file system. We can see how now there is like a high-level Hadoop API call in the Java code, which abstracts away a lot of the runtime information that we discussed earlier. Now then there's another Hadoop API call to fill in the buffer with the contents of the file. While DDLoader's programming model is a per block operation from the user, Hadoop's API is responsible for handling any file splitting under the abstraction of these APIs. They can then write the actual operation to be performed over the Hadoop file. Looking at the two programs side by side, we can see that other than the block level programming model, the two programs are mostly identical. And this is one of the main contributions of DDLoader, where we say that the user can provide a similar high-level program that they would write using the Hadoop APIs, while still being able to generate specialized code that would give better performance. We can now look at the code that was generated from that high-level interface. So we can see that we have a character array where now each element in that array has the concrete path to each block that makes up the HDFS file. And this was our rep annotated paths array that we looked at earlier in HDFS exec. Then the user written code to iterate over each of the blocks is also generates corresponding C code. And we can see that the x4 variable that has been generated is basically the iteration variable I. 79 corresponds to paths.length, or the number of blocks that make up this particular HDFS file that we are operating over. And similarly, x5, x6, and x7 are variables that are used to load the HDFS block from the underlying file system. Similarly, the user-provided operation over the HDFS file also generates C code that operates over this buffer. And as we can see, the buffer that has been read into is this x7 array, and we basically iterate over it, and if it's a white space, then we increment the counter variable x3. So far, we have described a single-threaded programming model where the operation specified by the user executes over each block of the file, one at a time. However, in a distributed setting, we want to be able to perform our computation over the file parallelly on different nodes that house parts of the file. And then we also want to have a way to accumulate this computation into a single node. In DDLoader, we achieve this using MPI. Unfortunately, DDLoader in its current implementation does not support automatic parallelization, so the burden is on the user to use MPI intrinsics that DDLoader does provide to properly parallelize the computation and aggregate the result. On the slides, we can see a simple example of MPI parallelization for the whitespace count program that we were discussing. On the left, we can see that the user simply initializes the MPI environment using MPI init, and then they have a MPI reduce call to aggregate the result over the different nodes. And simply doing this gives a speed up of 39 times over a single threaded execution for 64 processes spawned by DDLoader. Let's take a look at the complete execution pipeline of DDLoader. So, as we discussed earlier, an HDFS file is split up into several blocks on the underlying file system. In a distributed setting, we have different blocks of memory, each having their own CPUs. As discussed earlier, DDLoader uses MPI to parallelize its computation. So when the user executes MPI run to start the execution of their program, our generated program spawns copies of the program on each CPU that it wants to parallelize the computation over. The different blocks that make up the HDFS file are memory mapped into different RAMs. And if you note from the slide, a single block is never split across different RAMs, and this is by design of how DDLoader is implemented. The programs then execute over the blocks that are now stored in memory. Individual CPUs work on entire blocks, one or more. Multiple CPUs do not operate over a single block for multiple reasons, such as block sizes being usually very small, making communication harder, etc., etc. And since HDFS file splitting is not at predefined boundaries, there might need to be communication between the boundary blocks that are loaded into different RAMs. And this is also handled using the MPI intrinsics that DDLoader provides. And finally, the values computed across the different CPUs are then synced into a single CPU for the resultant output. So we compare DDLoader to Hadoop's Java and C APIs. The graphs on the slide are normalized to the speedup over Hadoop's Java API. We compare 3 different operations depending on the communication complexity. So whitespace count, which just passes around a single value between the nodes, character frequency, which passes around an array of length 26, and finally word count, where we pass around a hash table of arbitrary length. We do this for files of different sizes, 1 gigabyte, 10 gigabyte, and 50 gigabyte. And while we can see that the C API of Hadoop is slightly faster than the Java API in some cases, DDLoader is significantly faster than both. For a single thread, DDLoader is faster than the Java Hadoop API by a geometric mean of 11.79 for whitespace count, 1.93 for character frequency, and 5.33 for word count. And when we scale DDLoader, we can see that for 64 processes, DDLoader achieves around a 39 times speed up for most of these operations. If you notice, the single threaded speed up over the whitespace count program is much higher, and this is because the generated C program by DDLoader is trivially vectorizable by GCC. So we can conclude that generating a program that is aware of the distributed file topology can yield significant performance benefits. So future work. Flare is an accelerator backend for Apache Spark, written also in LMS and Scala. Flare retrieves the query plan from the Spark optimizer and then generates C code for the entire SQL operation. Flare, in its paper, was shown to outperform Apache Spark on a single memory system. However, Apache Spark is a distributed data analytics engine. So as future work with DDLoader, Flare might be able to specialize its queries over files stored in distributed memory and make an end-to-end comparison with Apache Spark possible. So in this talk, we demonstrated that it is possible to design a system that can specialize data loading for files stored in a distributed file system, and that using such a system, it is possible to generate code that would yield significant performance benefits by bypassing the abstractions that are provided by such systems. Thank you.
Thanks very much. Do we have questions from the audience? Yes.
So I have a quick first question just to clarify some understanding. In order to generate the relatively optimized code from the DDL language into the C language, I guess how much of the topology do you have to know? Do you have to know the actual paths that you're looking to query, like the actual strings?
Yeah, so you don't need to know anything other than the name or the relative path of the HDFS file on the HDFS storage.
Okay.
Everything else is, since it's like a later stage value, that is automatically generated in your generated C code. So the user just sees like a array that it cannot examine the actual values of when they write that operation.
How common is it that you do know the paths that you're looking to query in advance? Because I could also see a lot of applications where you don't know the paths of the files, you're working on arbitrary stored data.
I mean, I'm not sure I understand the question, because if you want to load a file, you need to know the path of that file, right? Maybe a clarification is, so there are 2 types of paths that we're talking about here. There is the path of the file relative to the HDFS layer or stored on the HDFS layer. And internally, that file is split up into like separate file systems, and those are like different paths. So the user knows this high-level HDFS path because they have to load the file. So they need to know where it is stored. But they don't know how that file is actually stored in your underlying file system. And that is what is automatically generated when we query the file topology.
Okay.
Back.
Thanks for the great talk. I was wondering whether you have any kind of initial results for the end-to-end thing by including Flare.
Yeah, so I implemented, not using this, but I hooked in the Hadoop APIs to Flare to see how it performs. And we did not get good results for that. We have not integrated DDLoader into Flare yet. But since we know that using the Hadoop APIs definitely is not the way to go, we are hoping that once we integrate DDLoader, we might be able to see better results.
Thank you.
Thanks.
Further questions? I just have one quick one. Not my area at all. So that means that anytime the topology changes, you need to respecialize these functions. Does that happen often?
It can happen, but that just means that you just compile the program again and restart your execution.
Okay.
Normally, in the case of, if you use the Hadoop APIs, there would be like some checkpointing. So you would perform part of the computation, and then if that fails because some node has died or something, then you would just like reverse the computation and do it again. And we would do something similar here, where we would compile the program again to our updated topology and then restart execution.
Okay, thanks very much. So if there are no final questions, let's end this session and thank